So a trolley is placed on a long ramp and is released from rest from the top of the ramp. It travels to the bottom of the ramp with a constant acceleration. Describe how a meter rule and a stopwatch can be used to determine the final velocity v of the trolley at the bottom of the ramp. So to begin with, we're going to measure a distance s using the rule, and we're going to time the trolley over that distance. And we're going to call that time t. We're going to use the stopwatch to do that, and then we are going to use the equation s is equal to v plus u, which is the over 2, which is the average velocity multiplied by the time. U is going to be 0, so that's going to give me s equals vt over 2, so 2s over t is going to equal to v. So a motion sensor is used to determine the velocity of the trolley at points x and y as shown in figure 21. The distance between x and y is 1.1 meters, and the trolley has a velocity of 1.3 meters per second at x and velocity of 2.5 meters per second at y, and you've got to calculate the acceleration a of the trolley. So this is a constant acceleration, so we're going to use the SUVAT letters, and I'm going to fill those in. So we've got 1.1 meters for s, we've got 1.3 meters per second for u, 2.5 meters per second for v. We don't know a, and we're after a, and we don't know anything about t, so select an equation that doesn't have t in it. So that's v squared equals u squared plus 2as. Rearrange to get me to being a equals v squared minus u squared over 2s. I substitute the numbers in, and that comes out as being 2.1 meters per second squared. So the frictional forces acting on the trolley are negligible. The acceleration of the trolley down the ramp is equal to the component of the acceleration of free fall parallel to the ramp. Use your answer to B part I to calculate the angle theta between the ramp and the horizontal. So if we look at the ramp, we've got the trolley on it. The G would be acting straight down. So if I look at the components of that, I can be parallel and perpendicular to the ramp. So I'm looking for the parallel one, so that's going to be G sine theta, and we know that that is equal to the 2.1 meters per second. So rearranging gives me sine theta equals 2.1 over G, therefore theta is the inverse sine of 2.1 over 9.81, which is 12 degrees.